Hey, my name is Jerry Cabazzuto from GodIsLoveTruthLife.com or GodIsLoveTruthFreedom.com because a life without freedom is not a life worth living. I'm also the founder of SoundPath.org, the first of its kind natural law-based hybrid online and in-person music and arts festival. Today, I am pleased to introduce a very special multi-lecture series on Equivalentics from my dear friend Leo, who I met in the ET extraterrestrial research community. Leo is a Pleiadean changeling who has been living among them and was given the green light from them to teach a kind of simplified quantum mechanics to humans, a knowledge base which has been partially shared with the scientific community in the form of quantum physics, and which explains the laws of reality in its true and infinite form. I've learned enough of this kind of quantum mechanics to the point where I am now understanding how important it is to share this knowledge with humanity. It's based on the laws of the universe. There are applications to the Hermetic principles, such as those of rhythm, vibration, polarity, correspondence, as well as to things like zero-point energy, interstellar travel, and remote viewing, and this is only the tip of the iceberg. The reason why we think it would be beneficial for the natural law community to release this information in particular is because we are a small group of caring and earnest truth seekers who don't require a government's version of ET disclosure, who think critically for ourselves and are open-minded enough to learn new concepts from benevolent civilizations. Feel free to check out a previous interview I did with Leo and our other friend Steve, where we discussed why living under natural law invites positive ET contact. No advanced civilization is going to want to befriend an immoral person. And no, they're not here to save us. If anything, all I've learned in my friendship with Leo is the need for humanity to get our shit together if we're ever going to want to evolve like other civilizations have in other realms. No one is asking you to believe anything here. This multi-class series is an invitation for you to go through the trivium process yourself so that you can familiarize yourself to this type of knowledge and consider being part of the team of pioneers leading eventually to actual ET disclosure while highlighting the science of the universe's laws, thus upholding our joint mission of supporting humanity's ascension process. This is a once in many lifetimes opportunity for humanity to learn about the laws of the universe from an ET, and it's for free. Enjoy.
So, in this equivalentic lesson, it's mostly an introduction. And we start from chapter 0, that's the way that we count. We count from 0 all the way to up to 100. In equivalentics, there is generally about 29 episodes, but this is no one ever learns the whole 29. It's usually 20. We'll see as we go on, and we'll see what fits and what doesn't. But we'll start from the first one, which is equivalation. Now, this chapter is made out of 3 lessons, and it is divided to 6, just to make it easier for the attention span. So in this chapter we have in the lesson 1 introduction. The first part is Mr. Alien and the Apes, we'll do it shortly. Mechanical machine, basics of equivalation, perfect line, introduction to the first dimension, your very first principle, the probability of the future, and why it works, did you know, and training exercises. So we begin with Mr. Alien and the Apes. Alright, so we have 3 triangles in front of us. These triangles represent all of human knowledge in certain aspects. So let's say we call the blue one physics, the yellow one mathematics, the green one biology. If you go from another perspective, we can call the red one, let's say, mathematics. So now, let's say I'm asking you just to try and imitate the process of finding all of those scientific fields to do actually the research. Now, we're not going to actually research stuff in physics, in mathematics, in biology. Instead, we're going to kind of simulate the research process by trying to find the surface area of each of those volumes. So anyone can tell me, how do you find the surface area of a triangle?
No, I don't recall how to do that.
Actually, it's very easy to find out. All you have to do is just ask Google.
Okay. And if we wanted to do it ourselves?
Just ask Google, how do you calculate the surface of a triangle?
Yeah.
So we're doing a training exercise, all of us together.
My audio didn't record on the call, but what I had said to the class was, we know that a square or rectangle surface area is calculated by base times height, and since we know all triangles are half of a square or rectangle, if one takes the base times height times 1/2, you get the surface area.
Yeah, I believe this is correct. Anyone want to see through Google if this is correct? Just to make sure.
Yes, I'm doing it now. I was just muted, sorry, one moment. How to find the surface area? Okay, to find the total surface area, it says triangular prism. That's okay, right? Calculate the area of all 5 faces, 2 triangular base and 3 rectangular sides, the sum.
No. Just the triangle.
Just the triangle.
Just each of those triangles.
Yes, just...
Because remember, each of those triangles is representing a different field in science.
Okay. Let's see. So to find the surface area of a triangle, multiply its base by its height and then divide by 2. Sure, that's exactly what Jerry said. Using the formula, area equals 1/2 times base times height.
All right, great. So let's give it a try. The base of the yellow triangle and the height of the yellow triangle is 224 times 84 divided by 2. One of you give me, use a calculator to find what that is.
Okay. So 224 times 84 and divided by 2, right?
Yep.
9408. 9,408.
So let's say we call it physics is how much?
9,408.
All right, good. Now let's try the red triangle. So the red triangle is, let's say, represented by mathematics. The base is 231, and we can already see that the height is similar, so it's 224.
So 231 times 224. Okay, let's do that. 231 times 224. Okay. So that says 25,872.
All right, so we called it mathematics, and that was red. That's how much again?
25,872.
872, great. And then we have the blue one. I'll just put it in a brighter color. There. Okay. And so we have also mathematics, which was, okay, let's calculate the base. The base is 246
246
times 224.
224. And this is biology, right? This is the science part?
Yeah, this is biology.
So 246 times 224. Okay, divided by 12. Okay, 27,552.
Yeah.
552.
Yeah, good. So we have physics, mathematics, and biology. Now let's see if we can get the rest of the sciences. Okay, so in this case, we have 231. So let's say we're taking physics. I believe this is something we've already seen before, 231 times 224. That was, I'd say, kind of the same like mathematics.
Yeah, right.
Check.
It was, yeah, it's the same. 231 times 224 was the mathematics.
All right, so we'll call it physics. And we're already seeing there that we have, again, biology and, oh, sorry, we have already physics, so let's call it mathematics, biology, physics, chemistry.
Chemistry, okay. Got it. Chemistry.
It's not something we're just making a simulation.
Okay.
So this is chemistry, and we already have the physics and biology. Okay, great. Let's look at the other triangles that we have. Right, so we have again, from that perspective, we can see a bit of the red, which was mathematics. So more or less we got everything. It's just different perspectives of it. Like mathematics looks different from the physics perspective. Chemistry looks different from biology perspective, and it would look different from physics. So more or less we got the idea of each of these triangles. Now here comes Mr. Alien, and he comes to all of these scientists, and he tells them that, listen guys, I don't know what you've calculated there, but it's all comes up to 27,899. 27,899. So all these scientists start telling Mr. Alien, no, we checked it, our numbers are correct, and we have for physics 9,408, for mathematics we have 25,872, for biology we have 27,552. So we checked our numbers, they're all good, they're very close, you were very, very close, but not exactly. And then Mr. Alien says, wait, you said physics 9,408, chemistry 25,872, biology 27,552. Guys, they're all the same. They're all exactly 27,899. And the scientist starts telling him, are you blind? Look at the shape of these triangles. They're not all the same. Yes, they may look a little bit similar from different perspectives, but they're definitely not all the same. So Mr. Alien decides to go, and he comes back again, and he tells them, okay, listen, here are 4 squares. Okay? You can see all of these 4 squares, And you can see that all of them are exactly in the same size, exactly in the same shape. Let's kind of glue these four squares on the triangles, and then you'll see that all of them are the same. So Mr. Aryan glues them into the triangles. Now the scientists here are losing their shit. They're saying, Mr. Alien, how the hell did you get here? You're blind. Can't you see that each of these squares are different? Come on. Look at that. They're all in a different shape. Some of them are even diagonal. What's going on with your ears? That square right next to that triangle, we can see that it's not the same size. Mr. Alien says, okay, fine. He goes and comes back. So the scientists obviously remove those weird additions that Mr. Alien added. And so Mr. Alien gives them a machine. The machine shows them exactly that if they measure each of these triangles, it comes out to be 27,899. Mr. Alien gave them the quantum computer that is able to calculate actual reality. And then here it is. Computer, we can see here 27,899. Next triangle, 27,899. Next triangle, 27,899. Wait, let's go to the next one. 27,899. They're all really the same. Okay, so the scientists are a little bit flabbergasted, but, maybe their machine is wrong. We've seen their trials with the rectangles. There's obviously something wrong with those aliens. So all of these scientists turn off the machine because obviously it's wrong. So let me show you what Mr. Alien sees that human scientists don't. Mr. Alien sees an extra dimension. So in fact, yes, all of these triangles are exactly the same. But the humans don't see two extra things that are very important. They're not seeing that square, and they're not seeing that square. The square on the top is equivalentics, square of the bottom is genetics, and they are the ones connecting all of these sciences. And while we tried many times to explain to scientists that they're wrong, they're just not willing to admit it. What they're looking at things is everything in either 2-dimension or 3-dimension. They don't even take into account the possibility that the 4th dimension is right here. It's not just an imagination. DNA is looked upon in 2 dimensions, while we are 3D entities. How can you expect to truly know how to affect the DNA in the right way without causing heart attacks and etc. if you're looking at it in a 2-dimensional perspective? Did everyone get the analogy?
Yes.
Yeah.
Okay. So the name of that quantum computer that was given to humanity, I believe it was in 2004 or 2005, we gave it a slightly different name than they use it today. So what we learned from this is that what this machine does is actually it is putting into the formulas that we give it both logical and illogical concepts and variables. And of course, it's taking into account infinity, which we can never truly grasp with our own logic. And what that machine does, it states if something is a fact or something is wrong, which means it could be, when it means unclear, it means that some of the results based on infinite variables came out wrong. And that machine is the machine that I gave in the analogy that gave them the numbers 27,899. So now we begin with the actual equivalation, understanding what it is. Now, I'm sure it's going to look to you like a bunch of kids' mathematics. Now, it is important that we're doing that reset to the most basic level, and later on you'll see that equivalation gets slightly more complicated. And even Jerry can tell you that usually the lessons they start very easy, kindergarten level, and then they go from 0 to 100 exponentially very fast. Isn't that right, Jerry?
Yes.
So before we begin, does anyone have questions on what we just went through? So yeah, you're right. Cambridge, not Oxford, my mistake. Cambridge, they're learning it as we speak. The one that there was an attempt with 3 of them in MIT, they just they're just like the rest of those scientists that when we just came with them and tell them that basically everything they thought was right is wrong, they don't want to be ridiculed. And they don't want to be a laughingstock because there is no way for them to prove it with normal ways. Although equivalentics makes sense in general, the MIT students were only taught a part of it, which kind of did lead to the breakthrough of quantum physics. So quantum physics here was not brought up by the aliens, but it was brought up, started I think with the string theory, which was a long time ago. So it wasn't really something that exploded in the scientific community and nobody really heard about it, but people started hearing about it like 15 years ago, 10 years ago, and that's more or less when the equivalentics lessons in MIT came to a conclusion. And that's where they learned for the first time about things that are bigger than infinity and ways to find the value of infinity. And of course, other dimensions. That's when quantum physics began to be in the headlines again. So you can say that these students maybe did kind of expose that information, they just called it in a different name.
Here I asked a question about how, since the scientific community isn't coming out with this knowledge because of fear of ridicule or, tenure positioning or whatever, it's important that grassroots activists like us in the natural law community who live by objective morality be the ones to release this information.
Yes, basically because I believe that you are not afraid to lose a reputation over trying to expose the world to a new way of thinking. I understand that the people from MIT just only learned a part about infinity. We're starting from the very beginning, and this can be proven more easily because we will be learning the basics, even the things that can be used today. I've even tried to use it to forecast the weather, and I made a better, I made a more accurate, although it was trial and error mostly, but I made a more accurate forecast for weather that was hitting the United States, like that snowstorm. I There is no way to prove it because it was for me trial and error, but I did tell Jerry exactly when it's going to hit them, which area is going to get hit the worst, and when it's going to leave.
Here I confirmed that Leo did indeed predict a recent snowstorm using Equivalentics.
No. Thank you.
So I'm hoping that sooner than later you'll be able to see in your own eyes why equivalentics is what proves all of these other scientists slightly off. But we begin with the very first things just to kind of reset. And I know it would look like kindergarten mathematics, but be patient. So we begin with just understanding what are segments and equivalated numbers. Yes, but I won't share everything because some of these are just explanatory and you don't really need it for later. So let's say this one just gives like a more introduction. There are like summary slides that I am sending later. So equivalentic numbers is subject designed to calculate the probability of improbabilities in a designated event or several related events. In short, an EQ measurement is either 0 or 1. 0 means probable, 0 means improbable, and 1 means probable. Now, calculation of a pair of event sequences, it is the absolute value of the first rounded value of an event sequence minus the second rounded value of an event sequence. Now I'll show you exactly how it looks like. Okay, if S1 and S1 is equal 6, S2 is equal 7, the event is 67. Then we we subtract 7 from 6 and we take the absolute value, which would be 1. So the equivalation is 1. The event is likely to manifest. Now let's take it one step forward. The numbers has to be one of the 10 only. 2-digit numbers must be separated into 2 different sequences. A fractured number must be rounded before use or used regardless of it being fractal. So for example, 675.8 is 676 or 6758. So let's take, for example, E974. I think I haven't heard Cynthia yet. Cynthia, can you tell me what's the equivalated number?
So I'm sorry, I'm having a really hard time seeing these slides. So let me see. So S1.
The event is 974.
Okay. So what are you asking me to calculate then exactly?
Try to find the Q, which would be 9 minus 7 absolute value, and then 7 minus 4 absolute value.
Oh, okay, I'm sorry. I was looking at the, so you said it would be 9 minus what?
Minus 7.
Which is 2.
And then 7 minus 4.
Which is 3.
Great, so the Q is 23.
Oh, okay.
It's that simple. Now, when we have when we are left with each of those event sequence, we need to continue the equivalation, just like a pyramid, all the way to the bottom. So let's say we take E67801. So we're seeing it as 6 minus 7, 7 minus 8, 8 minus 0, 0 minus 1, which would be the first equivalation sequence, 1181. Then the next one, since what we're doing is 1 minus 1, 1 minus 8, and 8 minus 1 is going to be 077. And then we continue towards the next line. Anyone want to tell me what's the next line?
To be 0?
The next line would be 0 minus 7, and then 7 minus 7.
Saying when that 0 or no?
What? Again?
Saying wouldn't that equal 0 or no?
It's not equal yet to anything. It's still just we're
Okay,
getting to the second line.
Gotcha.
So it's going to be 7, 0. And then we do it again for the last time. 7 minus 0 is 7. So that means that the final equivalation answer is 7 to the event of 67801. But this is an error. Why is it an error?
Does it need to equal 0 or 1 in the end?
Exactly, because it needs to be equal 1 or 0, improbable or probable. So what can we do about it? We need to acquire more data. Got the hang of it?
So how do you continue to break down the number 7?
So we cannot break down any more number 7. If we got to an error, it means that either we cannot calculate that event, something is wrong either in our formula or that event, or maybe we just need to acquire more data. So let us take it one step further. The perfect line. A series of 9 event sequences is called a perfect line. Since this event has the highest chance to produce an answer of either 0 or 1, no matter which sequence numbers we inserted into the formula. It is also making the very basic of indexes in the perfect indexions. We will learn about those in volume 2. Since this event has the highest chance to produce an answer of 0 or 1. And this is how it is done. Let's say I'm taking those 9 random sequences, and I'm starting to equivalate them. So for the first row, we get 18714133, and then 7163320, and 653012, then 12311, 1120, 012, 11, and 0. Great. So that means that the perfect line usually would give us something that is either 0 or 1. So we know that this event is probably correct. And that means that we can create a principle.
Well, I have a saying about that. Just hit my mind.
Okay.
continue. I'll explain that later.
Okay. So now we're going to do something like a class exercise. We are, say, let's see, 1, 2, 3, 4, 5. Yeah, and there are exactly 5 here. So I want you to all try it for yourself. So let's say Anil take the first one and try to equivalate it. Okay?
The first one, huh?
Because I can't do
The
this.
first one.
I'm lost right now. I'm just being honest with
What?
you.
What?
I don't feel like if you give me one, I can do it.
I showed an example of me solving one of the problems using a sort of written pyramid method to help the class.
I can tell you that even though I know the answers, I will do all of them together with you. Because it's also part of the humbling process for teachers, so they don't get corrupted. Okay, so Anil take the first one. Denise.
So it will be. Okay.
Well, we'll go at it together. Denise take the second one. Cynthia take the third one. Anika take the fourth one, and Jerry take the fifth one.
Just a quick question with the point there.
Yeah.
So, okay, just ignore the point for now.
Yeah.
Okay, thank you.
Okay, so 9 minus 7, that's 2.
Right.
Okay, 7 minus 1, that's 6.
Right.
Here's the question. 1 minus 5, that's 4, right?
1 minus 5 is 4.
Okay. 5 minus 6, that's 1. 6 minus 0, that's 6. 0 minus 9, that's 9. 1 minus 2, that's 2, and 2.
Now we go down one level all the way to the last point. I'm just looking for myself for a pen. Would that be on?
I have a quick question.
Yeah.
When we were doing this before with your samples, we didn't come across negative number, right? So
We always do the absolute value.
oh right, okay, fine. So okay, thank you.
Are we waiting for something?
Yeah. Did you get the final answer?
No, I'm doing my calculations still. I need more time, please.
No problem.
You want me to give you mine for the second one?
Yeah. Wait one moment.
Okay. Lou, do you want us to give you like the breakdown or just the final answer?
Just the final answer.
Okay.
Okay, I came to number 1 at the end.
So the event is probable or improbable?
Probable.
Great.
So I was correct. Good.
Yeah.
It took me long because I was looking for my notebook. Sorry for that.
No, it's fine. It might take other people longer, some faster. I can tell you that when I started it for the first time, I also got it wrong, and it took me like forever.
To be honest, mathematics is not my strongest point. I am strong in biology, chemistry, these things, but I try my best, and that's it.
Actually, here you mostly need basic calculus skills, and everything that you're missing, I can fill in.
Yeah.
You'll see later on that having background in mathematics is actually holding you back.
I see.
Because, for example, we don't use roots. Roots is wrong.
At all?
At all. We use something else.
Really? Okay.
Okay, so for the second one, I got 0. Improbable.
Alright. So actually it is probable.
Okay.
Do you mind putting in the group and sharing what you did so we can try and testing it?
Well, I broke down the brackets, which is 3 minus 1 is 2, and then 4 minus 2 is 2, 7 minus 8 is 1, 3 minus 2 is 1, and then I still had a 0 that I guess was by itself, so I just left it at 0.
No, so that's the thing. So it's...
That's what I wasn't sure.
Jerry did. Let me put for 0, but Jerry did.
Okay.
I'll share it. So the way we do it, we use every number that we have. So let's take the second one. See, 314278320. So 3 minus 1 is 2, 1 minus 4 is 3, 4 minus 2 is 2, 2 minus 7, 5, 7 minus 8, 1, 8 minus 3, 5, 3 minus 2, 1, 2 minus 0, 2.
Oh, I broke it. Okay, I skipped it. I didn't carry it over all the way like that. Okay.
Okay, we'll have plenty of opportunities to do it again, so don't worry about it.
Okay. I see what I did, though. That makes sense.
Okay, good. I think I gave...
May I say something?
Yeah.
There was a guy called Gauss, I think lived in 1700s, who said if you add 1 and 8, all the numbers, if you add them from the smallest to the biggest, they will, ultimately be from 1 to 9, or 1 to 10. Is that relevant or something?
In a way, just not to this part. It is used. I can tell you right now there's 134 ways to equivalate. We're using only one right now.
I see.
Remote viewers, when they do it professionally, they know about 50 ways to equivalate. I gave the third one to Cynthia or Denise?
You gave it to me. But I think I messed up. But I got 2, but I think I missed one of the subtractions that I was supposed to do, I think.
Yeah, that's okay, no problem.
But I got 2, was what I got.
Yeah, so actually the event is probable. Now I'll show the way to do it. I'll do it with an Excel sheet. let me just write it down. Okay, so it's going to be 9 minus 9 is 0, 9 minus 9 is again 0, so 0, 0, then 9 minus 1, 8, 1 minus 8, 7, 8 minus 7, 1, 7 minus 0, 7, and then 0 minus 1, 1. Then for the next row, it's deleting it. 0, 0. So 0, then between 0 and 0 is 0, then 0 minus 8 is 8, and then 8 minus 7 is 1, 7 minus 1 is 6, 1 minus 7 is 6, and then 7 minus 1 is 6. And then 0 minus 8 is 8, a minus 1 is 7, 1 minus 6 is 5, and then 6 minus 0 is 0, 6 minus 0 is 0. Next line, we have 1, 8 minus 7 is 1, 7 minus 5 is 2, 5 minus 0 is 5, and then 0 minus 0 is 0. Next one, we have 1 minus 2 is 1, 2 minus 5 is 3, and 5 minus 0 is 5. Next one is 1 minus 3 is 2, 3 minus 5 is 2, and then for the last one, 0. Oh, and we got there probable, so I guess there is a mistake.
Here I point out to Leo that he forgot to include the first 0 in the question.
Where? Oh. Yeah, so there is so it's 9 here. Okay, so yeah, we need to start over. I need to start over, so then 9, 0, 8, 1, 6, 6, 6, and then now it's 9 minus 0, 9, 0 minus 8 is 8, and 7, 5, 0, 0, and it's now 1, 1, 2, 5, 0, and 0, 1, 3, 5, and then 1, 2, 2, it's 1, 0, and 1. Okay, thank you, Jerry, for correcting me. Now this is very important because even I can make mistakes. Your job is to also make sure to point it out. Unlike in human teachings, the teacher isn't always right. I can tell you that many students in Equivalentics found better ways to do the same things the teachers were not familiar with, and it became a global sensation for us. Don't be shy to correct me. Cynthia, did you get more or less the same answers?
No, when I went back and finished it, because like I said, I had missed one of the subtractions, and then when I went back and finished it as you were doing that, I got 0. So I'm not sure why, but I got 0.
All right, let's go over it.
My final, the final equation was 2 minus 2, which equals 0 for me.
Yeah, so that's what I did as well, and then Jerry pointed out a mistake that I copied it without 1 0 at the beginning. So just look at the screen and tell me, if you can see the screen, Tell me if the numbers look the same to you.
So the first one I have here is 9008717. Wait, 900871771, and then
What?
But why I don't get why there's a zero in front. Because isn't the first one zero minus?
Oh, okay. Yeah. Let me put the event here. So here, this is the event.
Right. So that's the original number. But then, like after I did the first round of subtractions, then I got 900871771, and then the next round I got 9081666. Then I got 17500.
Okay, so here's the mistake. It's 9 minus 0, so it's not 1.
Oh, that's okay. I copied the number down wrong when I moved it down the line. Okay, that's
No problem.
Okay.
It happens to me, happens to Jerry, it's all good.
I just copied the number wrong. So at least I get it now, like how to do it, because at first I was like lost. Okay.
Oh, that's good, no problem. Next one, Denise.
No, I already went. You want me to do another one?
No, so maybe Annika?
Oh yeah, that one's me. So I got 0 improbable.
Correct.
Yay.
So, anyone know what that number is? The other ones are random. This one isn't really random.
Or number?
Or something? I can't remember. It's been so long.
314, that's pi, I think?
That's pi, exactly. And pi is very important for equivalentics. And for
Yeah, the Germans were building it. Yeah, the Germans were building the model.
yeah, so you'll see that later we will deal with it a lot. So you also learned something here. In equivalentics, we don't really care about the way you did something. For all I care, you can cheat as much as you want. What we care is about the result, and if you got it wrong, then you have to be prepared to show your way. That's it. This is not like mathematics, we don't care about the process. Because eventually, let's say I'm navigating, I'm flying my little spaceship in the galaxy, and while I showed my way and my way I've done it correct, but the results I got wrong, I end up face down into an asteroid. So results matter, yeah. What about the last one, Jerry?
Here I answer that I got the final result of 2, which means it is an error, since it is neither 1 probable or 0 improbable.
Yeah, correct. Error. So that means event is unknown, bullshit, wrong, the event is incomplete. So now we can maybe create ourselves a principle, something that maybe you can call it a cheat, but principles are a very important part of equivalentics. So according to the last exercise, we can perhaps create that principle. So a series of 9 event sequences is called a perfect line. So let's first understand what is a principle. A principle is giving us a formula we can use. It is always right, no matter what. That's it. And so a principle is something that is very important for entire science of equivalentics and science in general, because principles are giving us like anchors or steps that we can use in order to understand otherwise ununderstandable concepts like infinity. and things that are bigger than infinity. So principles are giving us like some ground to stand on. And also it's a more efficient way to solve an equation. So let's say our job is just to say which event is going to give us a probable or improbable answer, then maybe we can create a principle that will help us determine very quickly which event is more likely to give us a result or to be incomplete. So we took that event, for example. This is a perfect line, but we know that a series of 9 event sequences is called a perfect line, and it has the highest chance to actually provide an answer which is 1 or 0. But this one actually gave us 2. So this could be a good principle. A perfect line segment with at least one even and one odd number that are not 0 will always have a probability. Remember, principles have to always be right no matter what. So, unlike in human mathematics, we are taught in high school to prove it right, but the Pleiadean way of thinking is quite different. Now, although this is the first lesson, we need to make sure we can even use that principle. So you are now tasked with an actual research mission. Prove the principle right, which is very easy. You've done it in the tasks before. Now prove the principle wrong, and if you can't prove it wrong, explain why it always has to be right. It's a task for all of you. Try to prove that principle right, because we already seen, try to prove that principle wrong, because we've already seen that in the last tasks that it is right. It could be right. Try to do the other way around. So try to prove it wrong.
So it seems to me like every time, since it has to be a 0 or a 1 at the end, I keep thinking of like computer coding. Like computer coding is all zeros and ones, right? So everything inevitably has to add to a 0 or 1. And so you like have to make that happen.
Yes, right now we are kind of thinking like a computer, but this is only the first lesson.
I'd say it's very... Okay, yeah, go ahead.
No, go ahead, Emil. No problem.
It's very, when you go deep into natural law and morality, it is what it is. It's either here or not. That's the 0 or 1. You know, it's either exists or not. You know, it's not an opinion. So I say it's very, very similar, just different wording. You know, that's how we get to the principles of natural law. It's just the things you can do, because everything else is, you know, who knows what exists out there that it's your right or not. Just know the things you can do, prove the wrong, and you're free to go.
Okay, so if you cannot prove something wrong, then it must be right.
Exactly.
Can I prove it right?
Yeah, you can try, but we already did that in the last few exercises.
Well, does it also have to do with that there's not an odd number in that sequence?
No, it has to have at least one even and one odd. It can have 0, but it needs to have 9 digits, and it has to have at least one number that is odd and one number that is even. And
in the calculations. In the
event, in the line, in the first line that we start.
Okay, but there's no odd number there, right?
So because there is no odd number, it came out as 2, which is error.
Right.
But if
Right, so the
we
principle-
have here 1,
So the principle works.
the principle works. We know that it can be right, but can you prove it wrong?
No, I was just making the connection between that definition and how, I see what you're saying. Right. Well, because it doesn't have the
In order to use it, in order to use it for the future, we must prove that it is always right. Because otherwise we'll end up like mathematics. Like there is stuff like, for example, roots. You'll see that they're not always right, but mathematics still uses it, no problem. And that's a problem. That's a big problem because it means that some of the more complex calculations, like in physics, that uses roots a lot, is also probably wrong. Or
I see why that's important. I see.
It's like building on quicksand.
Right? So you must use principles that there is no excuse. They have to be always right.
So what's the question exactly? What's the thing we need to do?
The test is to see if you can like put different kind of numbers in the event, try to equivalate them, and see if you get the principle wrong. And
The event that we got, the 5 events.
the event of the nine digits, you need to put different numbers in it and try to get something that is not 0 or 1 using the laws here.
Okay.
We can just make up a number.
Just
So are we trying to get this right? Are we trying to figure out a way
we're
to
trying
get
to
this
get it
right?
wrong. We're trying to figure out a way to get it wrong.
But you're saying we could just make up a number, a 9-digit
Just
number.
make up a number.
Oh, you want us to come up with a equivalentic that's wrong?
Yeah, but it's not 0 or 1. That is, it's one of the other digits.
Okay. And you're saying that by using like all even numbers, because not having an odd number in it will make it wrong?
No, but that's the thing. We need to have at least one even and one odd.
Okay.
The goal is so that it doesn't come out to 0 or 1. That's the goal. Okay.
It is a huge
Now,
task.
if we cannot prove it wrong, then it means it always has to be right. Now, I'll give you a hint. Think simple.
Here I share my work where I use 9, a bunch of zeros in the middle, and 2 to show that the principle is wrong.
Yeah, see, so Jerry proved it wrong. Let's see if it follows all of these principles. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 digits. We have at least one odd number and one even number. And yeah, when it comes out to the end, it's wrong. So that means that this principle, we cannot use it because it isn't always right. So yeah, that's very similar to the result that we used in class. Just 5, 5, 5, 5, 5s, 2 still comes out as 3.
I put all 3s and then a 6 at the end, so would that be correct too?
Yeah. So that means that we managed to prove that principle wrong. And that's a very important skill, that it's not just reflecting on equivalentics, it's reflecting on every science that you see out there and every truth that someone tells you, this is the absolute truth for a fact. I hear lots of videos out there saying it's a fact, but no one ever showed you their way of getting to that fact. And so if no one showed us the way, then we have to try it ourselves. We have to prove them wrong. We have that responsibility as truthers.
Here I make a comment about how equivalentics is an analogy for natural law principles, that people either make objectively moral right or wrong choices, and there's no in between, and how these principles hold up through application.
Right. And even as natural law people, there are different perspectives on what is exactly natural law. And it is our responsibility to the next generation and to the people that we're trying to wake up and let them see that natural law is supposed to be natural, and they might not think like us, but we have to prove them that it's right, and we also have to show them all of our trials to prove ourselves wrong. And then it becomes undeniable truth. Okay, so that tells us that the so-called perfect equivalentic line is not as perfect as it seems. But it is not entirely true, because that is not the principle. The principle is a series of 9 event sequences is called a perfect line as it has the highest probability of providing us a linear answer, which is 0 or 1. And I think Annika said something about coding. This is basically introduction to the first dimension, which only has a result of 0 or 1. Now, this is not always. It is just very probable. And soon you will start talking in probable and improbable rather than possible or impossible. Trust me, this is something that also happened to me eventually. When people ask me a question that even if I'm 100% sure to be a fact, I'm saying likely or unlikely. Because the fun thing about the universe is that we never know all the answers. And I have been proven wrong many times. And one day, maybe you will see the fun in it. Being right feels great, but being wrong means you have something new or a new lead to research and find the truth. And at least to me, I found the journey to be much more exciting. So, how do we collect data for equivalation? What can be considered adequate data? Dates, hours, coordinates, social security numbers, product serial codes, remote viewing numbers. And so what cannot be considered adequate data? Names, words, letters, addresses, etc. The rule of thumb is, if the information can mean different things based on interpretation or by default, it's not good. So basically we can say that time is not exactly a good data string, right? Because on a planet that has a 9-day cycle, you can always take the local time calculation. But it might differ from planet to planet. We don't know the day and night cycle for each of those planets, but it doesn't matter because you're not living on that other planet. You always calculate it based on where you are. And that's why social security numbers, although they're not really defining who you are, your name might be given to someone else, but your social security number is unique, and it might not define you, but it gives you a certain perspective of where you are compared to everyone else. And that's why we also use coordinates. As, for example, a certain street may have the same name in different cities and in different states. Letters, like where, let's say we have 26 letters in the English alphabet, and I'm not sure about this, but Jerry, maybe can you tell me if the same number of letters in Spanish, do they correspond with the same letter of numbers in the English alphabet?
Here I answer that in Spanish, for example, the ñe, the N with the tilde above it, is considered an extra letter in Spanish. So technically, there aren't the same amount of letters in English as in Spanish.
Yeah, but not just the sum of it, but let's say the letter X, is it number 24 in Spanish?
No, because the number of letters are different in Spanish.
Yeah, but let's say the letter X, in English alphabet that's 24, right? X, Y, Z, yeah, 24. So is the letter X in Spanish also 24? No, okay, so you see, letters are also not good. Now, can you give me another example for one good data and one bad data?
The movement of the stars, because they move, they change places, so they may be interpreted in a different way throughout history.
That could be correct, but let's say if we're looking at it in a yearly cycle, so let's say if you're trying to calculate a historic event, then yeah, but in your lifespan, they won't change. But you are correct, because although you are basing yourself on the movement of the planets around you, that might not be the case for the movement of the planets in the galaxy, which it corresponds with your social security numbers. It is not defining you, but it is giving you a perspective based on your local area. So while you can use it in order to compare different results on Earth, it will be always more accurate to base it on the galaxy.
So it's a potential unless you based on the center of the galaxy.
Yeah. I mean, you can have a very accurate answer if you don't. But if you need something that is more historic, like you said, the movement of the planet changes, then you should just compare it to things that are older than Earth itself.
Right. It depends how much you want to go back.
So can you think of another good example for data and bad example for data?
I just started brainstorming different words. So I was wondering about instrument notes, like notes on instruments. So maybe like sound. Instrument notes being good data.
Yeah, they're good data. But in that specific category, there's also something that is bad data, which is guitar tabs. Because let's say someday in the future, let's say humanity gets wiped and a new civilization rises up, they will get to the same notes, but they might not invent the guitar, and then they won't have guitar tabs. So we always need to look at the grand scale of things. So let's say religion, basically, it is something that we cannot base ourselves at all, because if humanity gets destroyed and a new civilization rises up, they will discover chemistry again, the same way that we have chemistry today. They might give it different numbers, but it will be the same chemistry. Let's say hydrogen will have always one electron. It's not going to change. But religion, for example, it might change a lot. So it means that we cannot really rely ourselves on gematria, for example, which many remote viewers try.
Gematria, you said?
Yeah.
I want to bring that up. I mean, that's why almost in every language you have numbers for the letters, but you can see the difference as you explained previously. But the thing is, some languages are more in tune with shapes in nature. For example, that's why you have these names, like they call it the language of the light, language this, language now. So I'd say good data is shapes in nature.
That's true. That's perfect. Circles, spirals, triangles, squares.
Yeah, I was thinking geometry and like sacred geometry stuff.
What about color?
And that's vibration, yeah.
Well, color can be good data if you're comparing it to other things that are happening on Earth, because all humans see color the same thing. But there is an exception to it. What if we are comparing it to a dog?
Right.
Now, I want to bring up something. It's called spectrum of color in human vision.
Yeah, something like very narrow.
It's not very narrow. Well, it is very narrow based on light, but even the spectrum of color that the human eye can see is not exactly full.
So do you have full scale of colors, in general, in the universe? As you said, yeah.
Actually, yes. Because let's say our entire civilization was made of dogs, they would say our spectrum of color is all the colors that exist. But we see more colors than dogs. So there has to be maybe an entity that sees more colors than us.
You're right, yeah. Could it be infinite? I don't know.
Yeah, in potential, yeah.
I would think if you're talking about colors, it would have to be like the prism spectrum of like what you see in a rainbow.
What we see in the rainbow.
Yeah.
Ask a dog, it sees two colors in the rainbow.
Yeah.
Okay.
So that's why we need something constant all over the universe.
Right.
To be always.
So color might not be a good data, unless we of course compare it to other events regarding humans, but spectrums of light, like hertz, can be good data.
So what you are trying to compare it?
Yeah.
Yeah, continue. You're saying taking the self out, actually.
What? Again, sorry?
You're saying literally taking the self out, and anything that's personal, it could have potential. We need something constant to know exactly.
Right. Exactly.
Would
So basically,
would quantity be adequate data?
quantity of what?
Of anything, just quantity of something.
So essentially, yes. Everything can be good data. It's just compared to what. So if you're trying to calculate and when will an asteroid hit the Earth, then you need to calculate many variables. So which means amount of asteroids that are in potential to hit the Earth, the weight of those asteroids, their speed. We basically, in order to state like a random event, we need as much data as possible. And then we need to find a way to mix all of that data together. So this is what we're going to do in the last exercise of today, which is trying to combine different events into one final event that we can actually equivalent. Mass is great data, but even that is not always accurate because there is something missing in our physics. And correct me if I'm wrong, maybe it's already there, if anyone knows. There is something that we use in kinetics, which is volumetric mass and kinetic mass. Because objects in the universe, when they are, the bigger they are, the more gravity they oppose on other objects, and also their spin speed, which is the kinetic force, affects their gravity eventually as well. So mass on its own can be good when it's measured in the same gravitational field, but it might not be good in space. I can even give you an example from homeworks I have done in kinetics. Not really relevant to equivalentics, but just so you understand how far we need to go in when we start traveling in space. Let me see. So a ship is traveling at the speed of 7 py, doesn't matter, to a designated system. As you know, in space there are no brakes, so it needs to use quantum locking in order to park. Which planet will surely be one to quantum lock the ship into orbit after several revolutions without causing a dive-in? And which of the planets is the system's star? Now the data that we need to collect is kinetic mass, which is vibration, static mass, which is just mass, gravity inertia standard, space speed unit, volume unit, volumetric mass, gravitational pull, and kinetic presence, which means this is the, if there is a solar system, then there is a difference in gravitational effect based on the distance from the star and based on the distance from other massive stars like gas giants. So yeah, we need to take into account lots of things. Yeah, that's phonetics or kinetics, yeah. Kinetics is like physics above the speed of light. Oh, and by the way, the speed of light is not the fastest thing in the universe. And I think scientists here know that, but just like with the mechanical machine, they're not yet willing to admit that they are wrong.
Isn't sound?
Also, they measured it with a laser. What?
Is it sound?
No, sound is definitely much slower, but gamma rays are faster. For example, not that much faster, but this is one of the things that scientific tools of today can still detect, which is faster than the speed of light. So I've seen many videos. How do they explain that that nothing is faster than the speed of light? So if you take, for example, gamma rays and try to measure their speed, then you know for a fact that they are not faster than the speed of light because nothing is faster than the speed of light. So basically, they're trying to explain that dress is blue because it's blue. Great job.
Belief system.
Yep. All right, so I'm moving on, unless anyone has any more questions. Okay. Oh, yeah, I started saying about colors versus spectrums. So, like I told Cynthia, if you are trying to compare it with events that are happening to other humans that are seeing color the same way, then you can use colors normally. But if you're trying to compare it in events in the galaxy, for example, you should use hertz. And hertz are basically measuring wavelengths. And these wavelengths are the ones that are creating color as we see it, and sound, and basically any energy out there, including gamma rays. Alright, so now we're going to learn how to combine several different events with different variables in order to find the actual probability or improbability for a random event in the universe to occur. We are taking as an example something that can happen on Florida. So bus line 307461 will hit bus line B869. On this date, they're just working on a different date system, 5/6/23/245 at 1867. In the exact location of that, this is the coordinates. So before we begin that, I'll just explain what we're actually seeing here. First event is 37461. Now the second bus line B869, we cannot use letters, but in this case, we'll try and compare it with English. And we'll put, instead of B, we'll put 2. And then we have the date. So the date, this date is actually more accurate than the date that we are using, because their calendar is based on the revolutions of the galaxy. But it does create some problems, like seasons always happen in different months, because the seasons are affected by the local star system. And the hours that they're calculating is actually more accurate than ours. Now they have 28 hours in a day, but what's the more important thing is that they have 100 minutes in an hour. Now they're calculated the same way. An hour is calculated more or less exactly, but they're just counting it faster. And so the reason that it's more accurate is because whole numbers are always more accurate than fractal numbers. So 60 minutes in an hour, 60 seconds in you to calculate how many seconds are in 3 hours and 47 minutes, you need a calculator. But let's try it with 100, then it's going to be 34700. That's why it's more accurate. So the last event, the fourth event, 1867, and the coordinates, we're just ignoring those dots, and we get to that. So now how do we combine them? So the first thing we do is we refer to each event on its own. Let us try together the first event. So it's going to be 3 minus 7 is 4, 7 minus 4 is 3, 4 minus 6 2, 6 minus 1 is 5, 4 3 2 5, 1 1 3, 0 2, and QA is 2. Cynthia, want to try the second one?
I'm sorry, I was talking the whole time and I had it on mute. I'm sorry, I'm trying to see this. It's very hard for me to see this on my phone.
All right,
I don't know we're going to be looking at numbers this little. Okay, thank you. So which one? This one.
Yeah,
2, 8, 6, 9. So 2 minus 8 equals 6. 8 minus 6 equals 2. 6 minus 9 equals 3. 6 minus 2 equals 4. 2 minus 3 equals 1. 4 minus 1 equals 3.
Good. So the first event we together is going to be called QA, which corresponds to EA, and is 2. The second one, which corresponds to EB, is going to be QB, which is 3. Let us take the next one. Okay, the next one, 5 0 6 2 3 2 4 5. Oh, and that's important. Well, maybe, I'm not really sure, but you can see here the dates. So basically, we just add a 0. I won't go into unless someone really wants to know why we add a 0. When do we add ones? It has to do with galactic weather events that are affecting on the probability and improbability of general events that are happening in the galaxy. So I'm taking 5 0 6 2 3 2 4 5, and then 5 minus 6 is 1, 6 minus 4 is 2, 4 minus 1 is 3, 1 minus 1 0, 1 minus 2 is 1, and 2 minus 1 1. Next row, 1 1 3 1 0, 0 2 2 1, 2 0 1, 21, and 1. So QC is 1. Emil, can you try the ED?
Yeah, 7 2 1.
Good. And the next one?
5 1.
Good.
And 4.
And 4. So this one we'll do together because it's really kind of a nightmare. 1 2 2 3 4 1 1, 5 2 0 1 5 0 4, 1 0 1 1 3 0 4 3 2 1 4 5 4, 1 1 0 2 3 4 1 1 1 3 1 1, 0 1 2 1 1 3 0 0 2 2 0, 1 1 1 0 2 3 0 2 0 2, and all the way to 0. So QC is 0. Now what do? We combine all of the Q's that we're getting into the main event that we would call ME. So that's 2 3 1 4 0. Denise, would you like to try and tell us what's the final result?
Sure. 2 minus 3 is 1. 3 minus 1 is 2. 1 minus 4 is 3. 4 minus 0 is 4.
Okay, great.
1 minus 2 is 1. 2 minus 3 is 1. 3 minus 4 is 1. 2 minus,
Here,
yeah,
from here it's pretty easy to know that the final
there you go.
result would be 0. So,
You have an echo.
yeah, not sure why. The final result is that 0. This means that the event is improbable. So that means that
That they won't hit.
right, so that means that, yeah, bus line 37461 will not hit bus line B869 on this date at this exact time at those exact coordinates, but it doesn't mean that it cannot hit another bus on a different location on a different timeline. For that,
I have a question.
collect. Yeah, no problem. I'm just finishing the explanation.
Yeah.
We will have to collect the data for another event. Now, the longer the main event, which means the longer we have numbers here on the main event, the more accurate the forecast can be. So try to collect as much data as possible. In equivalentics, which is parallel to quantum physics, we take the principle of parallel timelines as a fact, even though it was proven unclear. And so we understand that everything that has happened before will happen again. We only need to calculate where we are on this infinite 10-dimensional loop. So what was the question?
But bus line B869, you change the B to number 2, right? From English.
Right.
But you said languages, gematria isn't that accurate, so it's
Right.
personalization. So
I know.
that's why you said you
I gave
have.
it as an example. I gave it as an example. The thing is that you cannot just calculate that random event. Bear in mind that equivalentic forecasting isn't used to calculate random events. It is used when you have an entire data collection on a possible event that has an unclear statistical answer, usually because there's too many variables, or if you have like a chance of 50-50. And you would like to check whether or not it is probable or improbable, and well, you just are out of all other tools. So only when you're out of all logical tools to check the probability, when it's entirely up to chance, this is the time to use equivalation based on the collected data. So why does it work? Because events are set on the universal pattern. All events are connected. So if the data is accurate, equivalation calculation may help you realize if certain events will occur according to the universal set of events or not, taking into account all related known and unknown variables in all of the dimensions at once. So do not take equivalation as an accurate measurement tool. It's a simple tool that helps you better understand the probabilities of events based on true and accurate data. It's an additional decision-making aiding tool. And the reason that it works in simple terms is that sometimes when it's purely up to chance, even then it might not be. It might be pre-written. in, let's say, something like the Akashic Records, but we don't know that, we don't have access to it. So we can use equivalation like a probe into the sheer randomness of the universe that can maybe give us an extra edge in understanding the concepts of infinity and absolute infinity. So based on that example, yes, the information is definitely incorrect because we translated the B into 2, and in every language it can be different. But this entire set of data is like a random calculation. If, let's say, we would want to see if those buses will hit each other on a place where there's usually lots of accidents with buses, then this question is more relevant. Get my explanation on it?
Yeah, I was thinking about there must be a way to know exactly.
Not random events.
This almost sounds like finite math. When I remember taking finite math in college, we did a lot of like probability questions like this.
Right, but eventually when it comes to a 50-50 chance, there is a chance that you need to take into account. And there is nothing that tells you what may have an extra edge over the other. Equivalation gives you that. I'll give you an example. Let's say, again, in space, which is a 6-dimensional structure, where are you located exactly? You don't really know. And everything still moves about 4 times the speed of light. So good luck finding where you are in just using normal coordinations. So I have a small explanation on what is that date that we're seeing, the 5/06/23/245. So this is based on the Grusietti calendar, and it is based entirely on equivalation, and with that and the Grusietti calendar, you may quite accurately forecast different kinetic weathers and where they will hit years in advance. The calendar has work days and off days. It's not related to your job, rather days that are statistically working better for you and days that simply may not. Following the Grusietti calendar is a proven and tested fact that in 676 days, your efficiency and success rates increase substantially anywhere in the galaxy, regardless of your local time it takes to complete a day cycle. And we have already also tested it with a few construction companies here on Earth, and all of them reported that after a year of testing, of trying to change the work days, not based on local timelines, and some of them worked in Saturdays, some took like an off day at the Tuesday, and then the next Wednesday, and after that they took an off day in different timelines. By the end of the year, they reported a decrease of 43% in work-related accidents, which is substantial. So if you want, I can give it to you later. It's not something you can use with your normal jobs, but if you're a private business owner, you can give it a try. Okay. So this is for your homeworks. This is something all of you need to solve. It's not just a few. The colors are just based on difficulty. Now for this event, the golden one, change the letters into numbers based on the English alphabet. So we'll all have the same result. And with this golden one, 12 to the power of half, in this case you ignore the S because it just represents a segment. And just take 9 digits in total, like the first one and 8 digits after the 0. And for the last one is calculate the probability of you being present at your house in exactly 14.5 months at sunrise. Now, when I'm saying you, take your social security number. Now, I don't want to know your social security number. I don't want to know the address of your house. I just want to know the end result. And since we have no way of actually validating your answer, make sure it's right. Now, to calculate 14.5 months at sunrise, from now, you need to find out exactly when will be sunrise 14.5 months from now, because it's changing. Now, if you're not feeling comfortable yet by sharing it because you're barely understanding or you feel like maybe people will ridicule you, that's fine. You'll get the true meaning of equivalentics in a few lessons from now. I'm going to also send the homeworks in the group. But it's not really related to this part of equivalentics. I can do it like after the recording. But wait, if you're still recording, I want to share with you one more thing. I shared it with just one of you, but I believe it's important for you to understand the perspective we're coming from. So this is a 3D construct, as you know, and us Pleiadians were coming from a 5D construct. Now, it's not just density or level of intelligence, it's an entirely different dimension. And I will explain now what it actually means. Alright, so let us go over it. This is the 3D sphere. Now, as you can see, it is kind of twisting, and no matter which perspective I'm looking at, the squares are changing their shape. This is how you can differ from 3D to 5D. So in the 3D realm, everything that you see to the distance will look much further than it really is. If you try to look at the building very far from you, that you have walked there before, you will notice that it seems like it's much further away. Compared to 5D, squares remain the same. Just the ones at the sides, they kind of twist. And that's how reality truly looks like. Now, just to prove you something that is called the PDT, physical dimension theorem, which is actually means that we experience all the dimensions in every reality that we are living in. We're just the level of understanding is what affects our ability to understand and see them and actually experience them. So this is a 4D perfect sphere. The fourth dimension is mostly referring to energy. This specific shape, I bet you have seen it before.
It's called torus, something like that.
That's a torus, yeah. So where did we see it before? Everywhere.
I'm sorry, what did you call it? You said trellis? What was that word you said again?
Yeah, so
spell torus?
T-O-R-U-S, torus. That's the name of the shape.
Yes, I got it, thank you.
So we call it a four-dimensional perfect sphere, and as you remember, we said something about perfect line. So this is kind of the same concept, that it has the highest probability to produce something. So basically, if I'll ask you something like that, is the universe perfect? Is biology perfect?
Our understanding of biology or biology in general?
Biology in general.
Let's say it's perfect.
It is efficient, but it's not perfect. Everything is changing. Everything is not really following the theory. That's why we keep discovering new things every day. So why do we use the term perfect? We are using the term perfect to describe something that is theoretical, entirely theoretical. So when we say perfect sphere, that means in theory, but nothing is truly perfect. Even the magnetic poles of the Earth, they make different shapes in the sky. That's the aurora borealis. They are not spherical, and they're not just one line. They are different lines, because even the Earth magnetic sphere is fluctuating at real time. It's not always spherical, it's not always perfect. And this is also important for people to understand, as someone has mentioned before, the Merkaba. The Merkaba is also not a perfect sphere. So that means if you're trying to aim for perfection using the Merkaba, you're bound to fail. Always give room for maneuver. Same goes for atoms, submolecular level, and even in the molecular level. They are following a certain pattern of circling the nucleus, but it's always kind of fluctuating. It's always changing. Even though it is based on the gravity of the nucleus, even on the subatomic level, it is not perfect.
What's the homework exactly again? We have to answer that question.
Yeah, no, we have 2 weeks for that because we completed both at the same time. I'll send that last one to you. I'll send it to the group. Now, I'm just saying, even those you are using here in this class, it's very important for your own personal safety. When you do the final one with the calculated probability of you and your house, basically your house, you need to find your coordinates. Don't tell them. Don't tell any of your classmates. I mean, even if you trust them, it's never safe. Don't give anyone your social security number or your exact address.
So we don't use our address, we use the coordinates for our address?
But again, you don't give me those. You just come up with the result.
Yeah.
Now, just to understand, I'll show you how to find your coordinates on Google. So I'm just going to take I'll open Google Maps, take a random address. So I'm taking this part here, and these are the coordinates. Got it? So what you do is just you can take it as 2 different events, as let's say EA and EB, or you can just use the entire line. Your call.